Hexanoic acid, which is also known as caproic acid, is a pretty stinky compound. It's a colorless, oily liquid, and its odor is often described as goat-like or like other barnyard animals. I think its odor is pretty similar to that of butyric acid, which is responsible for the smell of vomit. One major use of caproic acid is surprisingly in the perfume industry. As an acid, it smells pretty bad, but ester derivatives of hexanoic acid actually smell quite pleasant. For example, hexanoic acid can be reacted with propanol to make propyl hexanoate. Instead of smelling like vomit or barnyard animals, it instead smells fruity like blackberries or pineapple. To make the hexanoic acid, we will be carrying out a reaction known as a Grignard reaction. The Grignard reaction is extremely useful, and it allows us to create new carbon-carbon bonds. What's kind of funny is I didn't set out to make hexanoic acid in the beginning. I was actually planning to make something else, but I only found out halfway through that one of my reagents was no good anymore. Instead of scrapping everything, I just changed what I was making, and I'll talk about this later on in the video. This is the original shot that I took to show the chemicals that I needed before I knew that my acrolein had polymerized. Instead of acrolein, I use CO2, so I'm just going to cross off this bottle of acrolein, and we'll imagine it being replaced with a little bit of sulfuric acid and sodium carbonate. I start things off by adding about 5 grams of magnesium filings to a 500 milliliter round bottom flask. I've already gone ahead and attached a condenser to the middle neck and an addition funnel to the one on the right. On top of the magnesium was added about 0.2 grams of elemental iodine. Now for the solvent, I poured in about 80 milliliters of diethyl ether. When the ether is added, you can see it take on a slight orange color, and this is because some of the iodine is dissolving into the ether. On top of the condenser is placed the drying tube that's packed with anhydrous calcium chloride. This reaction is pretty sensitive to water, and the drying tube limits the amount of moisture that gets into the system. Now it's time to load the addition funnel, so I pour in 19 milliliters of 1-bromopentane. The 1-bromopentane in the addition funnel is then diluted with about 15 milliliters of diethyl ether. The addition of this extra diethyl ether dilutes the 1-bromopentane and makes it so the reaction isn't as vigorous. After adding the ether, it's pretty clear that the layers haven't fully mixed, so I take the addition funnel off and shake it around a bit. I then attach the hoses of the water circulator to the condenser, and I start cycling some ice-cold water through it. It's pretty important to use ice-cold water because as the reaction proceeds, the ether is going to boil, and if the condenser isn't cold enough, the ether won't condense and it will escape out the top. In the flask, before starting any reaction, we have an initial mixture of diethyl ether, magnesium shavings, and iodine. Before we add any 1-bromopentane, I place the flask over a hot water bath just to heat things up. Diethyl ether has a very low boiling point, so this hot water bath causes a little bit to boil, and you can see some of the bubbles coming off. The Grignard reaction can be kind of a pain to start, especially at room temperature, so by heating things up, we're giving it a little bit of a kickstart. Once we've brought the ether to a steady boil, I take away the hot water bath, and we're ready to start adding the 1-bromopentane. I open the stopcock, and I start to add the 1-bromopentane slowly. If the 1-bromopentane reacts, it's an exothermic reaction and heat is generated, so we should start to boil the diethyl ether. As I add more 1-bromopentane though, it really doesn't seem like very much is happening. I mentioned just a minute ago that Grignard reactions can be annoying to start, and I guess I'm having some troubles here. I decided to just keep adding more 1-bromopentane in hopes that the reaction would start. Eventually, I got to the end of the 1-bromopentane, and I was very sad to see that still nothing was really happening. It's really not uncommon for this to happen, and if it does, there's two main ways to get things going. The first is the lazy man method, and you just throw in a bunch more iodine, and the second is to grind the magnesium shavings using a glass stir rod. These methods are pretty different, but they do pretty much the same thing. When exposed to air, magnesium metal almost instantly oxidizes and forms a layer of magnesium oxide on the surface. In order for the reaction to proceed, we need to expose fresh magnesium metal, which can interact with the 1-bromopentane. Iodine disrupts the magnesium oxide layer and exposes magnesium metal chemically, but grinding with a glass stir rod does it mechanically. I decided to be lazy, so I just dumped in 0.2 more grams of iodine and turned the stirring to maximum. We start to see some ether dripping down from the condenser, and this is a good sign that the reaction has started. The yellow color of the solution that was due to the iodine also disappears, which indicates that it has been associated with the magnesium and it's doing its job. It doesn't take long for the reaction to really get going, and at this point, my condenser is getting overloaded. It's not very good when a Grignard reaction boils like this, because ether is just going to be pouring out the top of the condenser. We need to slow things down, and to do this, we use an ice-cold water bath. Our goal is pretty simple, and that's to keep it at a nice steady boil that doesn't overload the condenser. It's very important in this step that you don't keep the ice bath on it too long, though, because we can cool it down enough that the reaction stops, and we sabotage ourselves. When we take the ice bath off, though, the reaction might start to get much more vigorous again, so it's just going to be a cycle of icing things, taking the ice bath off, icing things again, over and over until the reaction's done. Anyway, in this reaction here, what we're doing is preparing the Grignard reagent. Schematically, it's a pretty simple reaction where the 1-bromopentane reacts directly with magnesium to form 1-pentyl magnesium bromide. This organomagnesium halide is generally known as a Grignard reagent. Grignard reagents are quite reactive in general, and they react quite readily with water. This is why we need to limit the amount of moisture that gets into the system using the drying tube, because moisture will react with the Grignard reagent and it will reduce our yield. It's also the reason why all of the solvents and the reagents that we use have to be dry. The 1-bromopentane and the diethyl ether are kept dry by storing them over molecular sieves, and the magnesium is dried in an oven. To further reduce moisture content, it's also pretty common to dry glassware in an oven before the reaction. Eventually, we get to a point where the reaction dies down and stops, and we have finished making our Grignard reagent. The next thing that we need to do is add in a molecule that we want to couple this Grignard reagent to. As I said before, my original intent was to couple it to acrolein to make 1-octen-3-ol. However, when I went to go in and use the acrolein, I found that it was polymerized, and let's just say I was slightly disappointed. I checked the acrolein a few days prior, and it was still a liquid and very usable, so I didn't bother checking it before I started this preparation. So long story short, I went to pour out and measure the acrolein, and nothing came out because it was completely solid. At this point, I had two options: just to smash everything, give up, and forget about the whole project, or I could try to run a salvage mission. I went through all of my chemicals to try to find something that I could react to make something cool, but I didn't really find too much. In the end, I decided to just react it with CO2 gas, because this would make hexanoic acid, which I thought could be cool because it stank, and it actually does have some chemical uses. There are two main ways to generate CO2 gas, either by CO2 dry ice pellets, or chemically using an acid and a carbonate base. It took me about 5 minutes, but I rigged together a pretty quick system. This system involved using two gas bubblers, where on the right I have anhydrous sodium carbonate, and in the one on the left I have calcium chloride pellets. The premise here is that I'll drip acid into the sodium carbonate on the right, CO2 will bubble out, go through that little red hose, pass through the calcium chloride pellets, which will dry it, and then this gas will be led into the reaction flask. In the addition funnel above, I've placed a small amount of 93% sulfuric acid drain cleaner. The reason that I use sulfuric acid here and not something like hydrochloric acid is simply because the water content is very low. If we use something like hydrochloric acid, we would generate more water vapor, the calcium chloride would have to absorb more, and maybe some would get into the reaction. I turn on the stirring, and I start generating CO2 gas by mixing the sulfuric acid with the sodium carbonate. It's important here to add the sulfuric acid slowly because we don't want to overload the system and overpressurize it. If too much gas is generated, we might pop one of our fittings apart, and this is obviously something we don't want to do. As we add more carbon dioxide, the reaction will heat up, and we'll be condensing back a lot of diethyl ether. This is another reason to go slowly because we don't want to overload our condenser. We'll also start to get a white salt buildup on the side of the flask. As more CO2 is added, the salt content will build up, and the reaction mixture will almost take on a white color. So anyway, here's the reaction that's occurring. The Grignard reagent that we made before reacts with CO2 to form the magnesium bromide salt of caproic acid. The salt is insoluble in ether, so it precipitates as the white solid you see on the sides of the flask. When we take a look at the Grignard reagent, we can see that the bond between the carbon and the magnesium is polarized. The electrons in the bond lie much closer to the carbon, so there's a partial negative charge on the carbon and a partial positive charge on the magnesium. The partial negative charge on the carbon allows the carbon to act as something known as a nucleophile. A nucleophile is an electron-rich chemical species that can donate electrons to an electrophile, which is electron poor. When a nucleophile donates electrons to an electrophile, a reaction occurs and a chemical bond is formed. Okay, so we have our nucleophile, which is our Grignard reagent, but we now need to introduce an electrophile. In Grignard reactions, the electrophile is normally the carbon in a carbonyl group. A carbonyl group is nothing more than a carbon bonded to an oxygen, but it does have slightly special properties. In the carbon-oxygen bond, the oxygen is more electronegative and it pulls the electrons harder. Like the Grignard reagent, the carbon-oxygen bond is polarized, but this time the electrons are closer to the oxygen and further away from the carbon. The slight electron deficiency gives the carbon a partial positive charge and makes it electrophilic. When the CO2 is added to the reaction mixture, the electron-rich carbon in the Grignard reagent will attack the electron-poor carbon in the CO2 and form a bond. This will give rise to our magnesium bromide salt intermediate, which will be converted to caproic acid in the workup. The contents of the reaction flask are poured into about 125 milliliters of water. I mix things around a little, but we're kind of left with a mess. This precipitate isn't soluble in either the ether or the water. I washed the reaction flask out a few more times using a little bit of water, but it seems like there's still quite a bit stuck in the flask. I prepare 150 milliliters of 10% hydrochloric acid, and I use some of it to wash the reaction flask. The 10% hydrochloric acid does a much better job washing the flask, and after washing it a few times, I completely cleaned it out. As I continue with the washings, you can see that the amount of the white precipitate in the beaker seems to also decrease. I'm using the hydrochloric acid here as a washing step, but it's actually a very important step in the reaction. As I mentioned before, the white precipitate is the magnesium bromide salt of our final product. When the magnesium bromide salt is exposed to acid and water, it gets hydrolyzed, and this forms our final caproic acid. The caproic acid that's formed is slightly soluble in water and quite soluble in ether. The addition of the acid also has a secondary purpose, and this is to get rid of any magnesium that might be left over. In general, Grignard reactions use an excess of magnesium, so it's pretty much expected to have some left over at the end. After all of the washing steps are done, I just add in the rest of the 10% hydrochloric acid solution. I mix it around a little and let it stand, and the last little bit of unhydrolyzed salt disappears. At this point, there's no salt that remains, but there's a whole bunch of bubbling occurring because the acid is reacting with magnesium. I just let it stand for several minutes, and when I come back, I'm left with 2 layers with a very minimal amount of bubbling. I transfer the contents of the beaker to a 1-liter separatory funnel. After everything's added, I wash the beaker with a little bit of water and diethyl ether to make sure that everything was transferred. At this point, there's still some bubbling going on in the upper ether layer, so I decide to leave it here until it completely subsides. I come back a little while later and there's no bubbling, so we're ready to separate the layers. I place an Erlenmeyer flask below the separatory funnel and I drain off the aqueous layer. The upper layer is the ether layer that contains the majority of our caproic acid, and we're going to transfer this to a separate container. The angle that I chose to use here was a little weird, so at the end it looks like there's 3 layers, but I can assure you that there was only 2. After our lower aqueous layer has been drained off, I transfer the ether layer to another Erlenmeyer flask. The aqueous layer is transferred back to the separatory funnel, and we're going to try to extract as much caproic acid as we can from it. The extraction process is pretty simple, and we start off by adding our extraction solvent, which is 50 milliliters of diethyl ether. Once the solvent's added, we take it off the stand, we cap it, and we shake it vigorously with frequent venting. Once we feel like we have an adequate mixing of the aqueous layer and the ether, we can place it back on the stand and allow the layers to separate. Once the layers have separated, we again drain off our lower aqueous layer. The ether washing is then combined with our ether caproic acid mixture in the other flask. This washing step is carried out one more time using again 50 milliliters of diethyl ether. The next thing that we need to do is dry our ether caproic acid mixture. Ether is generally not miscible with water, but it's still capable of dissolving a small amount of it. To dry things up, we need to use an appropriate drying agent, and in our case, I'm using anhydrous magnesium sulfate. If we were to skip this step and simply move on to evaporating off the ether, we'd actually be left with quite a bit of water in the product. I probably added way too much drying agent, so at this point, things should be relatively dry. The magnesium sulfate is separated from the ether solution by just filtering it through some cotton. The solution is filtered directly into a round bottom flask because the next thing that we're going to do is carry out a distillation to get rid of the solvent. After everything is filtered through, a small amount of ether is used to wash the flask as well as the funnel. I set up a fractional distillation to remove the diethyl ether, but I probably could have gotten away with just a simple one. I turn on the heating as well as the stirring, and then I insulate the column with a little bit of aluminum foil. It doesn't take very long for the diethyl ether to start pouring over. Once all of the diethyl ether had been removed, it's time to add what remains to a smaller flask. I transferred everything to a 100 milliliter flask, and I set things up for a vacuum fractional distillation. I pull a vacuum on the system, and then I start the distillation. Things start to slowly trickle over, and I discard everything that came over around 154 C. Once I got to the 154 Celsius mark, I swap the flask out for a new clean one. I pull a vacuum again and start the distillation, and at this point, we're collecting our caproic acid. At the end, we're left with an orange residue of higher boiling point stuff at the bottom of the distillation flask. In our receiving flask, we're left with an oily liquid, and I transfer this to a small amber glass bottle. The final yield of caproic acid was about 8 grams, which corresponds to a percent yield of around 45%. This is not the best yield, but it's honestly not too terrible either. The major loss is probably due to water being present and destroying some of the Grignard reagent. To have the most efficient reaction possible, we usually need to have the lowest water content possible, and this involves a lot of work. It usually involves drying all of the solvents and reagents overnight and then redistilling them. I'm not selling any products or doing any research, so this really wasn't necessary for me. Right now, I don't have any concrete plans to use the caproic acid in anything, but I'll probably esterify it in the future and make some nice smelling compounds. As usual, I'd like to thank everybody who's supporting me on Patreon. Everyone who supports me with $5 or more per video will get their name at the end like you see here. I've been saying forever that I would introduce some more rewards and, spice up my Patreon page a bit, but I kind of don't really have any ideas. If you guys have any ideas as to what might be feasible and good tier rewards, please let me know in the comments. Also, I'm trying to merchandise a little bit. I'm going to be making some NileRed branded beakers as well as lab coats. If you think this is a cool idea, let me know in the comments and maybe leave some suggestions as to how I could design things or, make it special or better in some way. Anyway, these are the videos that I've already filmed and the ones that I plan to film. If you guys have any extra suggestions, please let me know.